Okay, so here we are into Chapter 6, Gases, Liquids, Solids, and Intermolecular Forces. So we'll talk about the classic states of matter, gases, liquids, and solids, and how the particles are arranged, and similarities and differences there. And then we'll describe intermolecular forces, which act on all those different phases, but there are different types of forces depending on the composition of the matter involved. Okay, so looking forward to discussing this chapter with you as we have the others so far. Looking at our learning objectives for this chapter, we'll explain how the different properties of solids, liquids, and gases are related to the motion and spacing of atoms, molecules, or ions. We'll identify some differences between ionic and molecular substances and explain why these differences exist. We can make some predictions, as we'll see, about whether a substance would be expected to be ionic or molecular based on the temperatures at which it exists in each phase, for instance. We'll also classify forces between molecules as dipole-dipole forces, dispersion forces, or hydrogen bonds, which are not true chemical bonds, but are a very strong type of intermolecular force. We will also explain the effects that intermolecular forces have on melting points and boiling points. We'll explain why nonpolar solutes tend to dissolve in nonpolar solvents and why polar and ionic solutes tend to dissolve in polar solvents. We'll look at the 5 basic concepts of kinetic-molecular theory of gases, and we'll state the 3 simple gas laws by name and mathematically. As we said in the physical sciences, these laws tend to be short mathematical relationships. And again, theory, kinetic-molecular theory, theories are broader than laws, so we'll see how these laws fit into the kinetic-molecular theory of gases. Finally, we'll use any gas law to find the value of one variable if the other values are given, either explicitly or if we give you a way to find them. We'll state the ideal gas law and use it to calculate one of the quantities if the others are given. We'll, as we have so far in the course, we'll describe how green chemistry principle 3 must be considered in designing chemical reactions and processes. And lastly, we'll identify the properties that make supercritical fluids applicable in greener chemical processes. So I've talked about supercritical carbon dioxide, for instance, in the removal of caffeine from coffee beans. So we'll take a little deeper look at supercritical fluids here in this chapter. Alright, so hopefully this is review for everybody, but probably in middle school or even late elementary school you first discussed the differences between solids, liquids, and gases. Even early elementary school you use the terms, but probably not in enough detail to make much sense of it. So solids have particles that are in fixed positions and exhibit motions of vibrations. So the particles aren't free to move much. They can vibrate a little bit depending on the temperature. That vibration, as temperature goes up, tends to get more significant, and at low temperatures it tends to be very small vibrations. If we were able to reach absolute zero, there would be no vibration in a solid. For liquids, now we have particles that are free to move around within the confines of the liquid, so they can't escape too readily. The surface molecules can escape, we call that evaporation, but the molecules in the bulk, deep buried in the liquid, are not generally able to escape. They're able to move about, but they have to stay within the liquid by and large. And then finally, in a gas, you have particles that are very far apart and move randomly and rapidly compared to the other phases of matter. So we'll take a look at the picture there on the slide. It's grossly off in terms of scale. So if the solids and liquids are fairly close to what's going on, gases should be much, much further apart for anything at room temperature and pressure that we would encounter, because there's a huge deal of space between those particles, much more than we commonly show in something like the image there on the slide. Looking at some terms that we need to define in order to have a meaningful discussion of the states of matter. The melting point is the temperature at which a solid becomes a liquid, or at that same temperature the liquid would start to become a solid if we're going in reverse. We have vaporization, which is the process by which a liquid becomes a gas. And the boiling point is that special temperature where the particles of the gas, the liquid rather, can escape and become a gas from anywhere within the gas. And we normally talk about this as the so-called normal boiling point, which is the boiling point at 1 atmosphere of pressure. Boiling point does vary greatly with pressure, melting point not so much, but boiling point is very much influenced by the pressure outside. And so if you've ever baked a cake and followed the directions on the back of the box cake mix, you'll see there's high altitude instructions because the atmospheric pressure tends to be lower in high altitudes, and so the boiling point is lower for water, significantly lower, several degrees Fahrenheit. So the temperature is dependent on the external pressure, but when you're at the boiling point, any particle can escape from anywhere in the liquid to become a gas. And we ordinarily know this by boiling water and seeing the bubbles form at the bottom of the pot. The other process, evaporation, which is another example of a liquid becoming gas, that really just happens at the surface, and it happens below the boiling point temperature. So that's how puddles will form on rainy days, and then they'll evaporate. We never get to boiling, fortunately, here in Binghamton, but we do get our puddles to evaporate so that the liquid particles escape to become a gas through that evaporation process. Okay, if we look at condensation, that's the process by which a gas becomes a liquid. So if you're thinking about a fall day where you wake up and there's a lot of dew out on the grass, that's because the water vapor in the air condensed onto those grass blades to become a liquid due to the relatively low temperature. And that happens year-round, but it's very noticeable in the fall, for instance. We also have freezing, which is the process by which a liquid becomes a solid, and that occurs at the freezing point, which, as I mentioned on the previous slide, is the same temperature as the melting point. It's just how we're approaching the process. The melting point, we're going from the solid to the liquid. Here at the freezing point, we're going the opposite direction from the liquid to the solid. And then finally, sublimation is a special name for a process by which a solid changes directly from the solid to the gaseous state. So dry ice, which isn't ice at all in the sense of water, it's solid carbon dioxide. At room temperatures and pressures, sublimation is the preferred process, and that's why we call it dry ice. It doesn't leave a lot of liquid behind. The liquid that does form is water vapor that's condensed. If we go back to our first definition on the slide, it's just gas, phase, water in the air, water vapor that has condensed because of the cold temperature of the dry ice. But the dry ice itself, the solid carbon dioxide, goes directly to gaseous carbon dioxide, and it's a much more convenient process for things like delivery trucks where you don't want to have to open up the back and have a bunch of water pour out. Dry ice works really well. If we were at higher pressures, then it is possible to get liquid carbon dioxide, but at roughly 1 atmosphere of pressure, which is what we tend to be at, it's not possible to have liquid carbon dioxide. So sublimation is the preferred process, whereby at higher temperatures above -44 Celsius, the dry ice solid particles go directly into dry ice gas particles. Here we see what's known as a phase diagram. So we have, or at least a cooling and melting curve anyway. We have at the extreme left a solid, and the solid could be cooled down to theoretically absolute zero. But as you're heating that solid, the heat energy is going into the vibrations of those solid particles. So the solid's vibrating faster and faster as we warm it up. And then we hit our first plateau, that first level portion, which is called melting. That's because the energy now is not going so much into the motion of the particles, but now it's going into separating those particles, breaking up that crystal lattice for crystalline solids, and now allowing the particles to flow freely around each other like a liquid, which is what we end up with at the end of our melting line. So then now we have a liquid. If we continue to add heat energy into the liquid, it'll warm up. And then eventually, when we hit that boiling point, the liquid will rapidly vaporize, and now we see that the additional energy is not changing the temperature. We get flat again there, at the vaporization point, and that's because the energy is going into separating those particles. They were already free to move around each other in the liquid, but now we have to separate them by great distances to make a gas, and so that's where the energy goes. Finally, once we have the gas, we could theoretically continue to heat that gas to very, very high temperatures, and the additional energy goes into moving those gas particles faster and increasing the temperature, which is a measure of the average kinetic energy. So if we go in the reverse direction, we cool the gas, the energy goes into bringing the particles closer together until they're so close that they can condense, and then we see that additional energy that we're removing goes into a place where the temperature is not changing anymore because the energy is going into bringing the particles closer together. Once we finish that condensation portion of the phase diagram, we go to a liquid now that we can cool if we continue to remove heat energy, and then finally we'll hit the freezing point of that substance, and so the additional energy that's removed goes into just keeping the particles close together in more of a solid-like state where they're not as free to move until finally we have the solid. At that point, we can remove additional heat energy to decrease the vibrations of the solid in the solid state. So there we have it, the forward and reverse direction for a heating/cooling curve. If we think about the different forces involved in true chemical bonds, ionic bonds are the strongest of all those forces that hold matter in the condensed state. So ionic bonds, you have fully positive cations that are attracted to fully negative anions, and so on and so forth, forever and ever and ever, until eventually it terminates in something like a crystal grain. And these ionic bonds tend to be very, very strong. So if you think about table salt, that's an ionic substance, and you have to heat it to quite a high temperature in order to break it down. The ionic liquids that were discovered in the last few decades were a big interest in chemistry because these are substances that tend to be largely organic ions, and it's unusual that they would be liquid at room temperature and pressure because they do have ionic bonds, but the charge amount on the substance compared to the size of it is very small. So that's what allows for ionic liquids. When we tend to think ionic substances at room temperature and pressure, we tend to think solids because those bonds are quite strong. Now, if we think about intermolecular forces, so these are not true chemical bonds between one atom and another, but rather forces that build up across a molecule or even an atom, and dipole forces exist when polar molecules have a permanent partial positive and partial negative. So these are polar molecules, meaning they're not ionic, they don't have full charges that are plus or minus, but they have those partial charges like we talked about for substances like water. So the oppositely charged ends will attract each other and line up in such a way that we get a nice layout where the partial positive of one dipole is attracted to the partial negative of its neighbor, and this allows for these temporary interactions that make it easier for these substances to find each other and to stay together, and they tend to have therefore maybe higher melting points and boiling points than you might expect for small molecules of that size. Water is particularly small, H2O just 18.02 grams per mole per molar mass, yet it's a liquid up into 100 degrees Celsius. That's quite unusual. If it were not a polar molecule, it would not be expected to be a liquid at room temperature and pressure. It should be a gas by the size, but because it has the strong dipole forces, and as we'll learn, it even has hydrogen bonding, it's an unusual case. So dipole forces create a layout that allows for higher than expected melting points and boiling points because you have a new interaction to interrupt when you're trying to separate the dipoles in an ionic, or in a solid or a liquid arrangement. Once you get to gases, now they're too far away for the dipole forces to make much difference. Okay, so as I mentioned in the previous example with dipole forces, hydrogen bonds are extreme cases of dipole-dipole attraction. And we call them hydrogen bonds because they do involve hydrogens. So you have a hydrogen atom that's covalently bonded to a highly electronegative atom. So something that's far to the right and far up in the periodic table, such as nitrogen, oxygen, or fluorine. They have to be small because they have to be very strongly attracting those electrons within the bond, and therefore leaving that hydrogen with a strong partial positive and acquiring for themselves, the N, O, or F atom, a very strong partial negative charge. So it's a dipole. It's set up with polar portions, partial positive and partial negative ends, but it's such an extreme dipole that we call it a hydrogen bond because it very strongly is attracted to its nearest neighbor's partial negative. If we're talking about the partial positive, the hydrogen end of one molecule, as we see in the HF, is very much attracted to the fluorine end of another neighboring HF molecule. When we get to something like water, now we can attract in multiple places because we have the two H ends and the one O end that has the two lone pairs. We can get a nice arrangement. So water really is a very unusual substance. Not much of it in the universe, but fortunately lots of it on Earth. And it does unusual things like make these open layouts. As you can see, it sort of looks like a hexagon there, how the water's forming. That's why we get ice, which is mostly hexagonal ice on Earth, unless we have very extreme conditions where we can get ice that's more dense than its liquid. But typically, water as ice, as a solid, is less dense than its liquid because of the arrangement due to hydrogen bonding. We want to maximize those hydrogen bonding interactions, and that leaves an open structure to the ice that predominates on Earth. It's very important, obviously, for aquatic life in the winter that you get the ice on top instead of having the solid forming from the bottom. So that's one consequence of strong hydrogen bonding, is that we get the less dense solid than liquid for substances like water that have significant hydrogen bonding. But just recall, hydrogen bonding is not a true chemical bond, just a very strong case of dipole-dipole interaction. And the third type of intermolecular force we'll talk about here is known as dispersion forces. And these are exhibited by all molecules, but for nonpolar molecules, what you get is only dispersion forces, right? A polar molecule would get the dipole-dipole, and then an extremely polar molecule involving a hydrogen covalently bonded to an O, F, or N atom would undergo that extreme case we called hydrogen bonding. Dispersion forces, nonpolar molecules exhibit these, we call the dynamically induced dipole, where as the electron clouds of two neighboring molecules approach each other, they induce a dipole. They cause one to shift away from the electron cloud of its neighbor, and so therefore we do get a partial positive and partial negative temporarily set up in these nonpolar molecules, and therefore we do get a slight attraction known as a dispersion force. Dispersion forces are also known as London dispersion forces, named after the scientist London who did work on them. But the individual magnitude of a single dispersion force compared with a dipole-dipole or hydrogen bond is fairly weak. So the dispersion forces are the weakest. Traditional dipole-dipole slightly stronger, and then a hydrogen bond, that extreme dipole-dipole, the strongest. But when you think about a large molecule like octane, one of the components of gasoline, because it has those 8 carbons and it has a very large molecular weight and large electron cloud, you can set up a fairly significant dispersion force. And so on an individual interaction basis, it's small, but when you have a large molecule, you can get these small amounts to add up and up and up. And that's why we get things like oil having higher boiling points than water. Water has hydrogen bonding. The oil molecules have mainly dispersion forces, yet they have a higher boiling point because they are so large and they have so many dispersion forces interacting. So just because we say dispersion is a weak interaction, we have to be careful, because if you have significant number of dispersion forces in a molecule, it can give rise for large molecules to quite a strong interaction. So before we talk about how solutions form, let's just review solution definition from way back early on in the course. We said it's a homogeneous mixture of two or more substances. So it looks like a pure substance, but it's not really a pure substance. It can be separated physically by boiling off the water, for instance, in a salt water solution, and you'd be left with the salt. So it's a physical mixture of two or more substances, but it looks like a single substance. That's what the homogeneous part means. If we have a solution, we have a solute, which is the substance that is dispersed in the solution. So if we think of salt water, for instance, the salt, the sodium chloride, is the solute. And then the solvent, the substance doing the dissolving, which is usually present in the greater molar amount, so larger number of molecules for a molecular substance, this would be the solvent. So in our case of salt water, water would be the solvent. And water is an excellent solvent for ionic substances and polar substances. It does not do very well with nonpolar substances, where you think of the heterogeneous mixture of oil and water. Oil is nonpolar largely, and water is very polar, so they don't mix with each other, but nonpolar substances would dissolve well in oils, and polar substances or ionic substances tend to dissolve well in water. So you have to pick the right solvent or the right solute to get a solution to form. If we take a look here at the graphic, we have a picture of a solution. So you see those solute molecules, which are the red circles, the red spheres in our picture, are randomly distributed throughout the solvent, the blue molecules, the blue spheres, which are present in the greater amount. So we have an example of, say, a salt water or sugar water, I suppose, since we have just the molecular solute and not an ionic solute. So we have the red sugar molecules dispersed throughout the blue water molecules to form a solution. So as I already hinted at, polar substances and ionic substances tend to dissolve well with water, which is extraordinarily polar, whereas nonpolar substances tend to dissolve well in something like an oil that is also largely nonpolar itself. This gives us the guidance like dissolves like, or similibus similibus curantur, if you like your Latin. That's a guiding principle for us as chemists, and it says that solutions tend to form when both the solute and solvent have similar intermolecular forces. So if the solute is a nonpolar substance that really only has those London dispersion forces, then the solvent of choice should also be something that has primarily just London dispersion forces. So nonpolar solutes tend to dissolve well in nonpolar solvents. Likewise, polar solutes tend to dissolve well in polar solvents like water, and ionic substances tend to dissolve well in polar solvents like water as well. Of course, there are exceptions to the rule, but this guiding principle of like dissolves like gets you pretty far in chemistry, and certainly for this course we tend to follow that rule most of the time. Here we see an image of a salt crystal over at the left, the cubic sodium chloride crystal represented by the plus and minus ions, being surrounded by water molecules representing the dissolution process, whereby the water molecules orient their partial negative, the oxygen end, the red end, toward the plus, as we see at the top right, and the water molecules showing their partial positive, the hydrogen ends surrounding the negative ions, green minus signs, as you see at the middle bottom. So this is known as ion-dipole interactions, and it's what's responsible for many ionic substances dissolving in water or other polar solvents. So obviously, being polar, the solvent has a dipole, and being ionic, the salt breaks up into cations and anions, and this explains the dissolution of salt in water or other ionic substances in polar solvents. But not every ionic substance will dissolve in water or other polar substances, so just be careful. For the most part in our course, we'll assume that ionic substances will dissolve, but there are some important exceptions to ionic substances like silver chloride, for instance, that does not dissolve in water. Okay, moving on to the gas laws. So thinking of gases, we already mentioned that it's the phase of matter where the particles are very, very far apart. And so we can treat them almost like hard billiard balls, and that sort of idea of atoms being these hard neutral spheres works really well, and it works well because we believe the postulates of kinetic-molecular theory, which are one, the particles of a gas are in rapid constant motion, so they're moving so quickly and moving so randomly that they're not able to attract each other very much. The second postulate, the particles of a gas are tiny compared to the distance between them. So again, the pictures don't usually do this justice because the particles themselves are so small and the space in between is so large. The third postulate, there is little attraction between the particles of gas. We mentioned that a little bit in the first one, where they're moving rapidly and they're constantly in motion. There's such large space between them, number two, that they really have very little time to attract each other. So that's how number three fits in. Finally, we've got numbers 4 and 5. So number 4, the collisions between gas molecules are perfectly elastic. So when two gas molecules interact, they hit and recoil without losing energy. This is not quite true, but fairly true for most gases, at least high temperature gases. And finally, number 5, temperature is a measure of the average kinetic energy of gas molecules. So the higher the temperature of a gas, the faster the average gas molecules are moving in that sample. So these 5 postulates, again, give rise to that idea of billiard ball type atoms that are fairly representative of the molecules or atoms in a gas. So here we see a picture showing those gas molecules hitting each other or hitting the side walls of the container and bouncing off perfectly elastic collisions, and they're just change course and continue to move in constant random motion, and that's a pretty good representation of gases. Now as gases cool or the temperature goes down, obviously they're moving more slowly, or if they're under tremendous pressure, these are times when the gas particles really start to notice each other, and that postulate about them not interacting much starts to become less and less true, and you have the gases tend toward liquids, right? You can either cool down a gas or put a gas under pressure to liquefy it. So just be careful, the gas laws start to break down as you approach the liquid phase. But if it's a gas at a temperature well above the condensation point, then those gas law postulates tend to be fairly true. Alright, so the first of the gas laws that we'll talk about by name is Boyle's law. And Boyle's law, named for the scientist Robert Boyle, says that at constant temperature, the volume of a gas is inversely proportional to its pressure. So that's what we see in that first line. So V varies with 1 over P. So that's an inverse relationship. If we fill in some constant instead of the 1, we can say it equals. And then finally, that means P times V would equal that constant. We just multiplied both sides by P. And if we had two different conditions, we could say that V1 P1 equals V2 P2, right? Because we haven't changed the number of particles or the temperature, right? The constant temperature is part of our law. And therefore, if we had a set of conditions at one volume and pressure value, if we were to change the volume or the pressure, the other would change in a corresponding manner. So if we have a large volume at constant temperature without changing the number of moles of gas inside, we're going to have a certain pressure. And if we decrease volume, we'll increase pressure. If we increase volume, we'll decrease pressure. Or if we increase pressure, we would decrease volume. And if we decrease pressure, we would increase volume, again, keeping temperature and number of moles constant. So that's Boyle's law, and it's one of the gas laws, the first that we we'll go through by name. Here's a picture showing us some examples there for Boyle's law where we have different pressures. So in the first case, the one at the furthest left, we have 4 atmospheres of pressure, and therefore the volume is relatively small. As we decrease the pressure to 2 atmospheres in the middle and then finally 1 atmosphere at the end, the volume increases. So if we were to actually solve this thing, we could have pressure and volume values for each of those 3 conditions, and they'd all be equal to each other if we multiplied the pressure times the volume for each set of conditions. And finally, here's one last graphical representation of those pictures where we have the pressure 1 and the pressure 2. Notice as pressure goes down, pressure 1 is less than pressure 2, therefore volume goes up, since they're in that inversely proportional relationship. And if you go to the worked example folder under content, you'll see a worked example for Boyle's law. Okay, so here we just talk our way through it with this idea of inversely proportional relationships. There you'll see a problem solved with actual numbers. Okay, moving on to our second named gas law, we have Charles's law, again named for another scientist who worked on gases. And Charles's law states that at constant pressure and a constant number of moles, the volume of a gas is directly proportional to its absolute temperature. Notice that absolute. Here, going to Celsius isn't far enough, right? Fahrenheit we've already abandoned. We've mentioned Celsius as being the preferred temperature scale for the rest of the world outside of the US. And now we're saying it has to be an absolute temperature, so that if the temperature is doubled, for instance, we're not talking about going from 20 degrees Celsius to 40 degrees Celsius, because that's not truly a doubling. If you look at the Kelvin scale, that's our absolute scale, and there you're talking about the difference between 293 and 313 Kelvin when you're talking about the difference between 20 and 40 Celsius. So notice it's not a true doubling in the absolute sense. So just be careful that you're always using Kelvin temperatures, especially when we do gas law work. Some of the other problems you can get away with Celsius. Here in the gas laws, you absolutely must be in Kelvin. So we see there, because it's a directly proportional relationship, now we have V is directly proportional to T. And if we had some constant value, then we could say that V actually equals that constant times T. So therefore, if we divide both sides by T, we get our constant V all by itself. And again, like with the Boyle's law that we talked about previously, we could have 2 sets of conditions where we keep pressure and number of moles constant, and we get volume 1 divided by temperature 1 equal to volume 2 divided by temperature 2, noting that the volumes must be in the same units, probably milliliters or liters if you're using the SI system, and temperature must be in Kelvin for those T1 and T2 values. And here's a visual representation of those 2 conditions. So we have temperature 1 of being something like minus 100 degrees Celsius, but of course we would use the value of 173-ish Kelvin. And there we have a volume of, say, 30 milliliters. If we go up to 60 milliliters, notice now we're at something like 75 degrees Celsius, which again would be really something like 348-ish Kelvin units. So just remember, that's a doubling of volume and therefore a doubling of the absolute temperature, not just the Celsius temperatures. Alright, and here we see a visual representation of Charles's law. So we have a balloon, so that's your fixed volume of gas, and as we cool it, and the left with liquid nitrogen, obviously as the temperature goes down, the volume also goes down. And then on the right, we see as the temperature goes back up, the volume also increases. So we've only changed temperature, we've kept pressure and number of moles constant. So temperature and volume vary proportionally. in a direct relationship. And if you look at the worked example folder under content on Blackboard, you'll also see a worked example of Charles's law with some actual values if you're having trouble mathematically solving these problems. And the last of the gas laws we'll talk about, named after an individual, a familiar name here, Avogadro's law. There's also Gay-Lussac's law, but for our purposes, we'll just talk about the Boyle's, Charles, and Avogadro's laws. And Avogadro's law states that at fixed temperature and pressure, the volume of a gas is directly proportional to the amount of gas. And of course, with chemists being so fixated on that mole value, the amount that we'll look at is number of moles. So we see there volume directly proportional to number of moles, lowercase n. And if we want to change that from a proportionality to an actual formula, we'd have to say that the volume equals some constant value times the number of moles. And therefore, if we divide both sides by n, we can say that volume divided by moles equals some constant value, such that if we had two sets of conditions, V1 divided by N1 equals V2, a second set of conditions, divided by N2. And this should look a lot like Charles's law, right, where temperature and pressure varied directly. Now we have volume and number of moles varying directly. And so just as we mentioned with Avogadro's law that volume is directly proportional to the number of moles of a gas at fixed temperature and pressure, if that fixed temperature and pressure happen to be standard temperature and pressure, what we refer to as STP, notice standard temperature is 0 degrees Celsius, standard pressure 1 atmosphere of pressure, we find that a mole of gas, any gas, it doesn't happen to matter the identity of the gas, which is interesting. That's why those gases being treated as billiard balls really works very well. So any gas at STP occupies approximately 22.4 liters. Again, some gases deviate a little more from this value than others, but roughly speaking, any gas that you have 1 mole of at standard temperature and pressure would occupy 22.4 liters. And if you want to see some other solutions of Avogadro's law, go ahead and check out the worked example folder under content on Blackboard. So we looked at 3 gas laws independently. We looked at Boyle's law, Charles' law, and Avogadro's law. If we were to combine Boyle's law and Charles' law, remember Boyle's law was the P1 V1 equals P2 V2 stuff, and Charles' law was the V1 over T1 equals V2 over T2 stuff. Well, now we have P1 V1 over T1 equal to P2 times V2 over T2, what we call the combined gas law. And here we could choose to vary both pressure and temperature, for instance, and then see how volume changes. So instead of having just one variable at a time, here we could vary 2 species at once and still get something meaningful. So be sure to check out a combined gas law worked example under the worked example folder, which you can find in the content folder on Blackboard. Okay, and now if we want to really combine everything, so our combined gas law, so-called combined gas law, didn't really take into account number of moles like Avogadro's law did. Now we can combine everything to get the ideal gas law, PV equals nRT. It just rolls right off the tongue, that nice rhythmic series of letters. And so what that means is pressure times volume equals the number of moles times R, the ideal gas constant, times the temperature, remember, the Kelvin temperature. So since we know that at standard temperature and pressure, so STP, and remember standard temperature for this value is 0 degrees Celsius, but of course we would use the 273 Kelvin value. We want the absolute temperature. So at 1 atmosphere of pressure and 273 Kelvin, standard temperature and pressure, 1 mole of any gas should, as long as the gas behaves ideally, should take up 22.4 liters of volume. So if you use those 4 values, you're able to solve for R, and R At least the R that we'll use is 0.0821 liter atmospheres per mole Kelvin, right? To isolate R, we had to divide PV by NT, and that's why our units are units of volume and pressure in the numerator and moles and Kelvin temperature units in the denominator. So we'll use 0.0821. 0.08206 is a little more exact, but again, that's the ideal gas constant, and that works for the ideal gas law, which goes hand in hand with kinetic-molecular theory that says any gas should behave the same way under ideal conditions. So certainly be sure to check out Blackboard, the content folder, and then go into the worked examples to see an example of an ideal gas law solution for those having any trouble mathematically solving for either P, V, N, or T. R is a constant, so you wouldn't ordinarily solve for that one, although I just told you how you could verify R by looking at 1 mole of an ideal gas at standard temperature and pressure, knowing that it should occupy 22.4 liters. So there you have it. Hopefully this review of the different phases of matter and the gas laws in particular and intermolecular forces has been fruitful for you, and if you're having any trouble with the math that goes along with all of this, hopefully those worked examples help to clear things up. Otherwise, certainly please contact me.